All right, guys, we're back. Today we're doing lesson H.03. And what we're going to do now is build upon the general stuff that we worked on last time. And we're going to try and develop a vector equation of a line. So you've had point slope, slope intercept, and point slope, slope intercept, and standard. So now we're going to give you a vector equation of a line. Let's start here. If A, point A, is a point different than the origin, so it's not at the origin, then the set of all multiples of A is the line through the origin and the point. So to demonstrate that, I've set up quadrant 1, and we're going to plot a point. We're going to plot the point 4, 2. So this is point A at 4, 2. All right, no big deal. Now, what is a multiple of A? Well, let's say I took point A and I multiplied it by 2. So 2 times, and I'm going to call this point B. Point B is at 2 times 4, 2, which would give me 8, 4. Okay, so let's plot that. 8. So here's the point B at 8, 4. Well, let's do it again. Let's do point C at 3 times 4, 2. So that's a different multiple of point A. And what we get here is 12, 6. So that's 8, 9, 10, 11, 12, up to, and there's point C at 12, 6. Well, what you should notice right now is that I can draw a line through the origin up through the 3 points. There's the first part. There's the second part. And there's the third part. And notice they're all on a straight line. Now, I didn't have to use times 2 or times 3. I could have used fractions. So like 1/2 times 4, 2 would be 2, 1. So any decimal or fraction is going to fill in all the points along here. And if I go to negatives, it's going to push it down into quadrant 3. So if A is a point different than the origin, then the set of all points that are multiples of A create a line that goes through the origin. All right? Simple concept. Let's build on it. All right. But what happens if the line doesn't go through the origin? Well, what now? So what we're going to do is we're going to draw a line that goes through 3A. So here's point A. I'm sorry, not 3A, 3, 1. That's what I meant to say. And B at 8, 2. So there's 3, 6, 7, 8, and -2. So here's point B at 8, 2. And that defines a line. So we'll draw the line. So there's the line, okay? How do we know if, oh, can you see that? How do we know if P at 13, -5 is on line AB? So let's say I gave you these 2 points. I said, how do we know if that point's on the line? Okay, well, one thing, which would be really easy to do, is just plot the point 13, -5 and see if it's on the line. Now, of course, that wouldn't be the fun way to do it. We want to use math. And I haven't drawn my x-axis long enough to get out to 13, and I did that intentionally. So we're going to use math. Here's what we're going to do. We're going to move the line to the origin. So we're going to move the line to the origin. by subtracting point A from the line. Okay, that may seem a little confusing, but it's not. Look, here's point A, all right? And it is at 3, 1. Okay? We're going to subtract point A from it. So point A minus A is at 3 minus 3 is 0. 1 minus 1 is 0. So I just took this point and I went over 3 and down 1. That was the subtracting motion. So minus 3 minus 1. And it took me to the origin. So A minus A is at 0, 0. So I moved point A. Now I got to move all the other points on that line. Well, there's an infinite number of points, but I really only need to move one more. So we're going to move point B by going left 3 and down 1. Okay, so that gives me this point at B minus A, and its new coordinates will be 8 minus 3 is 5, and negative 2 minus 1 is negative 3. Well, look what we've done. We've defined a new line. And it goes through the origin. Okay, so now let's go back to this concept up here about heads and tails. Heads minus tails, or multiples of a point. We're going to see if I go P minus A, that would be equal to, now P is 13 minus 3, that came from point A, parenthesis, oh no, I got that wrong, hold on. We'll do it this way. So point A is at 13, negative 5, and I'm going to subtract point A, which is 3, 1. I just got a little ahead of myself there, because that is equal to 13 minus 3, negative 5 minus 1, which gives me 10, negative 6. Okay? Now, what do you notice about the point 10, negative 6? Isn't it a multiple of 5, negative 3? So if the translated point P is on the green line, then the original point P must be on the orange line. And we've shown that it is in fact on the same line because it's following this whole multiples thing. So we can say if P minus A is a multiple of B minus A, then point P, the original point P, is on line AB. And I did that just by taking the original line, moving it down to the origin, checking to see that P minus A, so that relocated point P is on the green line. So if the relocated point P is on the green line, then the original point P must be on the orange line. All right? So let's see where that takes us. In general, if point P is on line AB, then P minus A, now this is getting really confusing. So this is a point, and if it's on a line, then P minus A, remember A is another point, is a multiple of B minus A. And there is a number K such that, okay, now this is where we get interesting. So I've got the point P minus the point A equals, now it's a multiple, right, of B minus A. So how do we express that being a multiple? We have a scalar factor. K is the multiplier. We call it a scalar multiplier. So if P minus A equals some number times B minus A, we can say therefore, the three dots is therefore, P lies on AB, the line AB, if P equals A plus K times B minus A. So now if you think, how did I go from that to that? See how that's minus A? I just added A to both sides. Okay? P lies on that, this point P lies on the line AB if all of it fits into this equation. And that right there is the vector form of a linear equation. So you've had standard, point slope, slope intercept, bang, there's your fourth one. The vector form of a linear equation. Just keep in mind, all it's saying is that the point P will lie on the same line as A and B.